So if anyone has newly tuned in or just kind of wants a recap, what we're doing is trying to create this cool smoky particle effect. And the way we've done that, I think I will kind of go through and comment this code a bit. So we're using processing to do this, which you can download for free on processing.org. It's an open source, like freely available thing, and it's a framework built around playing around with graphics in like a cool, arty, easy to use way. So what we do is we kind of load some of our basic image assets here, and then we set up a particle system. And we gave this various parameters. So we kind of defined the box in which the particles can be spawned. We defined the initial velocity, or the ranges of initial velocity these things can have, so they're moving a bit left and right, and they're also moving like up at some sort of slightly varying speed. And then we kind of define some some visual stuff for them. I feel like these actually make more sense being grouped together like this. Not the most redundant comment I've ever written, but you know, it helps to make these things clear. Then we did spawn some stuff initially. I don't think we actually need this anymore since we actually sort of automated that within the particle system itself. We also don't need this. Oh, hey, Blazing Fish. What do I call you? Thank you. Yeah, I'm really pleased with how this effect looks. It's got a fairly natural, smoky appearance already, and it's actually super simple the way we built that up. So hopefully, as I walk through now, how this works, we can, hopefully it will make sense to you. And let me know if you have any questions or any details which don't make sense. So the first thing we do every frame is we calculated how many seconds had passed since the previous frame, because this was important for making sure the spawn rate and the physics doesn't vary depending on your frame rate. So if you have a really fast computer with a super high frame rate, we don't want to move things more quickly. We want to move them actually a smaller amount each frame, because there's more frames, right? So we kind of want a consistent appearance even if the frame rate's different. So then we drew our background layers. And then we actually updated and drew our particles. And we bundled all of this stuff up to do with spawning particles into this particle system class. I wish I could reorder these, because in my mind there's kind of a hierarchy here, right? We have our main code, which contains particle systems, and then that contains particles, but yeah, this will have to do. So we had a function here, fairly self-explanatory, which just spawns a particle somewhere in this random range of positions, which kind of defines the box, and with a random velocity vector there. We set its lifetime and its image and its color, then we added it to this internal list which we're holding here. Then each frame we keep a kind of counter of how long it is since we last spawned the particle, and then comparing that to the spawn rate, we work out, hey, should I spawn one or more particles on this frame or not? So we kind of had spawning first, and then we had updating of the existing particles. And then on the draw, we just kind of delegate the drawing to each individual particle here. Then the particle itself, all that it does on the update is we did a bit of simple physicsy stuff here, which is that we update its position, which is stored in these px and py variables, so its x and y coordinates according to its velocity, and we scaled that based on how long it's been since the last frame. So if it's been, if the velocity in the x direction is 10 pixels per second and it's been, 2 seconds, then we're going to move it 20 pixels on this frame, for example. So that's where we're at right now. And it gives us the kind of effect that we like, right? So the box where these are spawning is actually slightly off the screen down here because it means we don't get them visually popping into existence as we spawn new particles. They spawn down here and then they just kind of drift up into our field of view, so we get rid of any like pop-in effects. But there's one major issue with this code right now, and when I went to get my marmalade bagel just now, I did not leave this running, and there's a very good reason for that, which is that there is a horrific kind of, I guess you could call it a bug, but there's a horrible performance thing here which would cause this thing to get slower and slower and eventually like fall over and die. Does anyone know what the big issue is with this program right now and why it's eventually just going to completely kill my computer? Okay, so the reason for that is that inside our particle system, yeah, blazing fish, that's it. There is a memory leak in this code. And the reason for that is that in our particle system we have a list of particles, and we're just happily spawning them away, 100 every second or something like that. And then when the particle's old enough, it kind of fades out and we stop drawing it at least, but that particle just stays in that list kind of forever. Just taking up space, and eventually my whole RAM is going to get completely tanked and destroyed by all of these particles, and it's going to be a terribly bad time. So let's think about what this looks like right now and what we'd ultimately prefer it to look like. So right now we have this particles list. And it starts off as like an empty list, and then we spawn a particle, and then we spawn another one, and another one, and another one. And then these things are updated, and eventually their lifetime runs out, and they're faded out, and we stop drawing them, and they're kind of dead. But the next particle still gets spawned over here. So this list is getting longer and longer and longer. And this is a textbook memory leak, right? Like this list gets bigger and bigger, and all this dead wood just sits around here, kind of taking up space and RAM, and this list gets longer and longer. And yeah, it's just going to eventually like use up all my RAM or crash the system or make things run slower or all of the above. So what it would be nice if we could actually do is, there's two ways to go around this, right? Like one is, hey, when a particle is dead, we could just like remove it from this list. But there is, and that would work. That would be a simple kind of solution to this, but there's a slight issue. You can kind of see by what I'm doing now, right? Is like if I want to remove it from a list, I kind of have to do all this work to like do something with that space and kind of get rid of it and then shift everything else over to kind of fill the gap. What might be actually nicer for us to do is instead, what if we pre-created a list of like a big enough size? We know what the spawn rate for our particles is. Let's say we figure out that the maximum number of particles we're ever going to have, given the spawn rate and given how long they last, is like 10. Watch me fail to draw 10 boxes here. I think that may actually be 10. So what we can do here instead is start, use this space for a particle and another, 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 and another. And then when we get to this point, instead of what we would do before, which was to just add another particle to the list, we can come back around, and by this point, hopefully this one has expired, and we can, instead of creating a new particle, we can just repurpose this one. Right, we can kind of reset it back to the bottom of the screen and reuse this again. And this would typically be referred to as like pooling. Oop. And again, this is a super common thing in games for things like bullets. Like if you got a bullet hell game or a shmup or something, anytime when hey, there's never going to be more than a certain number of things, and we don't want to deal with like adding and removing stuff from a list, we just pre-create a big enough block of memory for them and just like somewhat intelligently kind of try and reuse this. And the way we typically go around this is we'd kind of create our array. I'm going to draw it smaller this time because I can't be bothered to draw 10 boxes. is we'd kind of keep like a little pointer here to, hey, where's the next like open slot? So when we spawn the first particle, we'd go, okay, there's the slot. Then we're gonna move our little pointer up, you know, and then when it's time to spawn again, we spawn it there, and eventually we've filled this thing up. And when we put the last one in, we just kind of cycle this pointer back to the beginning. So let's try and implement something like this now. So now what we want to do, when we spawn a particle, rather than creating a new object, what we kind of want to do now is pre-create all of these objects, but just have some of them like turned off, like ready for us to use in the future. So I'm going to create a little initialize function here, which is going to pre-create a whole list of particles, but just have them all like turned off. So I think I'm going to actually add a little flag into this class. Called is alive. And I'm going to say I'm going to set this alive flag to be off when it's dead. So if its life remaining is less than or equal to 0, then I'm going to say, hey, I'm no longer alive. And then in here, I don't need to repeat myself. I can just say if we're alive, then we're going to draw it. Otherwise, we're not going to do anything. So now back to our system here. What we kind of need to do is decide how many particle slots we're going to have. So we can be intelligent about this. We can look at, hey, what's the... okay, maybe we can do this. So we can try and calculate what's the maximum number of particles we ever are going to have like on screen at any one time. And I will suggest that that is equal to the spawn rate multiplied by the lifetime. So working through a couple of examples, if the spawn rate is 10 per second and the lifetime is 10 seconds, then we're going to have 10 times 10 or 100 kind of maximum things. I may have like an off by 1 error here, but we can fix that later on if that's the case. And let's also like round this up because these are floating points and this is an integer. In fact, I'm going to put this in a separate variable because it'll be useful to in fact, okay, so the reason we use this array list is because it gives us this functionality to just add stuff on add and remove stuff from it. But given that we're going to have a fixed size chunk of particles now, I think instead I'm going to use just a regular old array for these. And then what we want to do is fill it with these particle objects, but kind of leave them in their not alive state. Yeah, blazing fish. So the reason I'm using an old array is that if we know it's going to be a certain size, then why not just allocate an array of a fixed size? Also, it means I can then just use the length to loop through it later on, and I don't need to like store this max particles variable somewhere else. Honestly, you could just use an array list and like add stuff into it. And that might give you a bit of like a safety net if maybe it's hard to predict exactly what the maximum number of particles is. You could just, you know, look for a dead particle to reuse, and if there aren't any spaces, you could still just add one to the list. That's another kind of approach that's a bit more flexible. But given that we have a kind of fixed spawn rate and lifetime of these particles, I can just predict it. So if it doesn't need to resize, then I guess an array fits that like perfectly well. So we're going to store a new particle in here. It's going to be super explicit here. Initially, the particle is not going to be alive. So now when we come to spawn a particle, we don't want to add a new one to the list. We want to pick one out of this existing list and just set all of the properties inside it and set its alive flag back to alive, basically. One other thing we're going to need is a kind of pointer or like an index to like what's the next particle we're going to spawn. So this is going to start at 0, right? So we're going to, the first particle we spawn is going to be the 0th, or, you know, particle 0, or the first particle in the array. Then it's going to be more or less the same, and rather than add it to the list, we're going to like make sure it's, you know, flag it as alive now. The next thing to do is to just increment this next particle index. There, okay, so there's an issue here, which I'm sure Blazing Fish you've probably already spotted, which is, hang on, what if this index like goes off the end of the list, right? We kind of need this to wrap. The whole point of this was that we would, you know, use this slot, then this slot, then this slot, then this slot, then this slot, and this slot, and then wrap back around and use the first slot again. So the typical way to do, yeah, exactly. So I could just be kind of like explicit here and say, if we're at the last point in the array, and set it back to 0. I could use modulus to do this, and typically I would, but I feel like just to be super explanatory, I'm going to do it this way. Okay. Now what we can do is throw a couple of checks in here. We only want to update a particle if it's alive. Similarly, you only want to draw a particle if it's alive. I think I was already checking that in here, so I can kind of get rid of that check since the particle system is now sort of managing that for us. Okay, fingers crossed this works. I mean, I've just made a pretty major structural change here, so there's every chance that this is going to screw up somehow, or like, you know, I miscalculated this, so let's see what happens. Okay. I've realized already I never called this init function. And, you know, I can be a bit more defensive perhaps and say, do it in here so I don't have to remember to do that myself. Another way, of course, is to move these things into a constructor and call init there, but I'm kind of being a bit gung-ho here with a load of public variables and stuff, so, you know, this will work for me. There's a few things we could do. So we could look at, one option is the movement of these particles and the physics of them. Right now they're moving at a constant speed and they don't really accelerate, but if they're like these light drifty things, then maybe they should get kind of blown around by the wind a bit. That's one thing we can look at. Another thing is they're always a kind of constant color, right? Like they fade out over time, but they're always kind of like a grey white color. We could play around with, you know, what if they started out grey but then got like blacker over time, right? Like to have like a kind of sooty effect. This is really nice for fire, right? Like maybe you want them to start out red, you know, yellow, and then go like red and orange and grey and black to have that kind of thing going on. And as we move on to embers, which is something else I kind of wanted to get to eventually, that sort of thing becomes more important. I think one thing I may talk about is a bit more physics stuff, right? Like, what if we want these things to not always have the constant velocity? So to kind of recap this, we have our particle here, and it has a certain position, you know, it's at a certain x and y, and it has a certain velocity. But if we want it to like gradually accelerate upwards, right, as if it's being lifted up by some wind or something, then this doesn't quite do it for us because our velocity is static. Another thing to add to this kind of hierarchy, our physics hierarchy here, is the idea of acceleration. So position is just, you know, the coordinates where this thing exists. And what we did was velocity was every frame we updated the position, basically by just adding the velocity onto it. Acceleration has a similar relationship where we would add the acceleration to the velocity every frame and change that. And then thinking about the units, the position is just a position in pixels. The velocity is it has a certain speed in pixels per second. And acceleration is pixels per second per second. Which is kind of a weird unit and maybe kind of a weird concept, but this is the fundamentals of physics, more or less. So if you remember our good friend Isaac Newton, who introduced us to this famous equation, F equals... F does not equal that. F equals ma, where F in this case is a force, m is a mass, and a is acceleration. So this can kind of be confusing to people, but I think a nicer way to think about this is you can do a bit of mathy stuff and reorganize this equation to say F divided by m equals a. And to me, this is more intuitive. What this basically says is, you know, as we apply a force to something, it's going to accelerate it, right? Like if I'm pushing something, then it's going to speed up in the direction that I'm pushing. But if I'm pushing something really heavy, then the force is going to have less of an effect on it, right? Like if it weighs 1,000,000, if it has a mass of 1,000,000, whatever, then I'm going to be accelerating it less than if it's like a feather with a mass of like 1. So that's kind of intuitively what this represents. And if we have a particle again, think about the forces kind of acting on it. A typical force you might think about is like gravity, which you typically think of as like pulling something down. Yeah, right, like to me this is a way more intuitive like version of this equation, because like mass times acceleration, like what does that mean intuitively? I don't know. But F divided by m is like the force, but like toned down according to like how heavy the thing is. So if we have a particle and gravity's pulling on it, then in this case the force is gravity, right? Divided by m equals a. So let's say gravity is applying to these particles. What might this look like in code? So one thing I'm going to do quickly is move the box of these spawn like up again, so it's a bit easier to see. Take a look at this. Okay, so these things are popping in and they have an initial velocity we give them, and that's what causes them to go upwards. If we want to get a bit more physicsy with this, then we need to think about these things as having a mass as well. Since it's like a physicsy thing, it probably lives up here. We want to make sure we pass that through. Call this 1 for now. Okay, so here's the point where we're taking the velocity and basically just adding it onto the position. And we can do something very similar with acceleration, where we just take the acceleration, which in this case is... So gravity doesn't care about x-axis, like left and right, so we'll just call this 0. Does anyone know the acceleration of gravity? So if you remember from physics classes, gravity on Earth is like 9.8 meters per second squared or something like that. But since this is like in pixel coordinates, none of that really applies, so I'm just kind of gonna arbitrarily pick a number of 10 here. What we can do now is add that acceleration onto the velocity, almost in exactly the same way as we add the velocity onto the position. With the only difference is that we also divide it by the mass. So let's take a look at these things now. Yeah, interesting. So you see what's happening is that these are spawning with a slight upward velocity, but then they're eventually the acceleration over time is like gradually like slowing them down, and eventually they'll start moving downwards. So this kind of effect might be nice for like, I don't know, something coming over the edge of a waterfall, like that kind of sprayy, hazy thing, something like that. But what I really want to do here is kind of a hack, is like to have these things actually move upwards and kind of accelerate upwards. And a nice easy way to do that is to give these things a negative mass. So gravity is effectively like now pulling these things upwards. It's a very not scientifically accurate gravity. To me that feels a bit too fast, so let's make the absolute value of that smaller. Still kind of crazy, maybe we can go super small with this. Yeah, like they're just gonna like drift up. In fact, I should be making this higher because of the way the math works out here. Yeah, so maybe it's not a super obvious effect, but there's just a bit more like variation, and these things don't have a totally like constant speed there. Now as they get like wispy and less dense, they just get kind of carried off and disappear and kind of separate into clumpy bits like that, which is kind of nice. Now if I move these things back down, honestly this would probably have no like real visual effect, but the reason I kind of wanted to get this in there was because further down the line with some other effects, having this foundation of acceleration and stuff in there will actually allow us to do a whole load more interesting stuff later on. So one thing I kind of want to do is make the sprite actually a bit bigger. They're still a bit like clumpy and bally. So if I scale this up, and by the way, this is kind of like a smooth texture we're using for these particles right now. If I drew something out, I could make a more like cartoony effect or something like that. if I'm doing that, I probably need to make sure they spawn like even lower. Okay, cool. That looks pretty good for me for a nice smoke layer. So now we've got this layer of smoke. One thing we can do is, you know, think about adding another particle system possibly, and kind of layering these things up. So instead of having one, let's now introduce a list of these. In fact, I'm not going to do that. Because I kind of want to draw them in a different order in relation to these other layers that we have here. So let's make this our like background particle system, but then I have another one that appears in front of our engineer sprite. So with a bit of reordering here, okay, we've now dropped this stuff behind our engineer. I don't know if you can really see that on the stream, but he's kind of layered nicely on top of that. So then let's make another copy of this to put in front of him. Bit of copy and paste magic. Again, this is super hacky, and in reality I'd use some kind of like config file or something to do this. If this was a nicer IDE, I could do this way more easily. I always debate, right? Like when you're doing this kind of copy and paste hackery, like there's a point where you should figure out how to do it properly and like write a script to do it, or a macro, or do some like regular expression-y thing. But sometimes, you know, that quick hacky copy and paste works just fine. So I've got another layer front here. So let's play around with making these a bit different. So maybe our rear layer should be like a bit less dense. And maybe more like, maybe more faded out, but maybe like have it last for longer. And it's really up to you, like how you do this, really. I'm totally just fiddling around for my own enjoyment right now. Yeah. Yeah, you're right, Blazing Fish. So I feel like we have a pretty nice system for this basic smoke going on that we can work with here. So let's think about adding another layer to this thing, which is this Ember Layer, which we kind of talked about. This is where things potentially get a little bit more fancy. And let me open up Steamhounds again to kind of show you what it is we're trying to recreate here. So frame rate is not awesome, but you can see we have these little flecks which are floating around, and maybe you can't, maybe it's hard to notice, but there's some fancier stuff going on with these. The first one is that their color is changing over time. So if we try and follow a particle, you'll see it kind of goes from like a yellow to an orange and then to like a black, which is kind of emulating what a little ember or like mote of stuff that, you know, a fire kicks off does. And also they're not moving in a straight line, so again with the low frame rate this might not be coming across super cleanly, but they are kind of swirling around in a more kind of a realistic path. So there's a few things going on here which you can try and build up step by step. So first things first though is that we need an image for these particles. And this time they're going to be pretty small. And again, even though these are going to appear, like orange and red and stuff, I'm going to draw them in white because that then allows us to use the code to mess around with the color later on. So what I'm going to do is, I'm not an artist, so forgive me. Just draw a little fleck like that. Yeah, that'll do. I'm going to call this Ember particle. Okay. I think what I may do as well is drop the rate of these right down so that nothing messes with our frame rate as we're adding this next thing on top. So since we're going to be fiddling around with these, I'm going to start off by drawing them again like more in the middle of the screen so we can see clearly what's going on as they spawn and stuff. Yeah, that's fine. I'm going to give them a 0 mass because you want to focus on the new stuff really. This time we're going to load our Ember particle. And I'm just going to draw these in white because we're going to do something a bit more fancy with these. Let's draw these on top as well. Let's see what we've got to begin with. Okay, I'll be honest, I can't see anything there. What's going on? I've divided by this mass at some point. I've divided by 0, almost certainly. So actually the way to do this is to make these Yeah, another schoolboy error. Okay. Okay, this is cool. Got these kind of things floating around. Again, they look like dust motes or something like that, maybe. So let's have these float upwards to begin with. Maybe a bit slower. Make them orange, yeah, right, that's the idea. But the thing is, I don't just want to make these orange, I kind of want them to change color over time, like go through a gradient. And there's loads of ways I can do this, but I think... Why didn't the console scream about that error? Oh yeah, that's a very good question. So, generally speaking, dividing by 0 is a problem, but it's not like a crashing type error. You'll just end up with a number which is like infinity or like not a number or some like special value. It might be nice if it actually like threw an exception if you divide it by 0, but generally it just gives you an unreasonable answer rather than just like crashing out or throwing an error. Well, I guess the issue is that it's quite hard for the compiler to figure out. You know, if I put this at 0 here, there's quite a lot of steps this goes through before it actually divides by it, right? It would have to work out, oh, you know, did they ever change this 0 to something else? Or, do you see what I mean? So compilers can get pretty smart and they can figure out some of these errors sometimes, but there's a limit to how much time they're going to spend like analyzing your code in like super detail to figure out these kind of things, which theoretically maybe they could, but in practice it gets difficult or like practically impossible in a lot of cases. Okay, so let's think about having these things change color. And I think the way I want to do this is actually to use an image which kind of defines the gradient of color we want this ember to go through. So I'm going to make a tiny little narrow little strip of an image here. And then what I'm actually going to do is just straight up like color this in. So maybe we want it to start out white, like just initially, and then kind of go like yellowy. Sure, there's a nicer way to do this with like a soft brush. Again, I'm not an artist or like an image editor, so forgive me if this is a really dumb way to be doing this kind of thing. Let's have it kind of go a bit yellow, and then through orange. There's always a dumber way, Ita, as I've discovered many a time. Yeah, right. This is super flexible, and I could do this in a more codey way. The reason I'm doing this is it's because something an artist could more easily like play around with, like in a visual editor or something like that. Then maybe you just want it to go like grey and dull just at the end. Yeah, so what I'm literally going to do is load in this image, and then based on how long the particle's going to be alive, I'm going to look up a color. Use this as like a lookup table, essentially. So I'm going to pick out a color. So at the start of its lifetime, yeah, right. This is a very kind of flexible approach, I think. and then maybe we want this to like fade out at the end as well. Let's save this in here. I'll call it Ember Lookup. Yeah, so I could have an option. So my existing particle system is just gonna be a fixed color. So I could have something where, you know, there are different modes that this can run in. So it can be like a fixed color mode or like a color lookup mode. What I'm gonna do is just create another image, which is just like that mid-gray color. And kind of use the same. Use the same thing for the main smoke. So let's load these in as well. Oh, okay. So what we're seeing here is, because I want these things to also fade out over time, so we're actually just seeing like this image editors, that's how it's showing that it gets transparent. So that's all that is. Because I also want to look up like the alpha value from this texture as well. Yep. So rather than color, we want another image here. Okay. Thank you, Blazing Fish. I'm glad you're enjoying it. Okay, so now we're passing through this image into all the particles. So these should use the smoke lookup. Yeah, awesome. Thank you, Orzinio. I'm glad you're enjoying this as well. And this last one should use the Ember lookup image. Cool. So now the slightly more fancy part of making this lookup pattern. So let's go back over to the diagram here. Oh, it's getting kind of busy now. Okay, so we now have our lookup image, which is a narrow, thin strip of pixels. That. And we also have the idea of the lifetime of the particle, right? Like how kind of between like 0 and 1, I guess. Like 0 is at the start of its lifetime and 1 is right at the end. And we need to kind of look up a position in this image. We need to, we need to read a particular pixel based on how far along the particle's lifetime it is. So the y-coordinate's easy, right? The y-coordinate's always 0 because it's just a 1 pixel high image, and then the x-coordinate is 1, 0, 1, all the way up to the width. So the simple thing to do is just do, if this is, what do we call it? Like let's call it the progress of the particle through its life. So we can just do the width of the image times by progress. Can anyone see that there's a slight something we need to account for here, which is a bit like somewhat annoying? And it's basically, it's that this may not always be an exact pixel, right? Like, it may be that our progress is actually like, I don't know, like 0.7 or something like that. So what we're... Yeah, so in this case the x is like how long the particle's been alive for as a proportion of its whole lifetime. So if the particle's living for 10 seconds and it's like 5 seconds through, then we're going to look up the pixel like more or less in the middle of this image. And we can do that, but the slight issue is that we may not land on an exact pixel here. So what we probably want to do, like if we're trying to read from, what would be like the pixel 0.7, we kind of probably want to like do a bit of a blending between these based on like the exact progress. Right, so if you've got 2 pixels next to each other, and in theory they have like, each has like a middle point. If the color we're trying to look up is actually here, then we need to do some kind of blending of these 2 things based on like somehow like the ratio between them. So maybe that'll make more sense when I get into the code here. So we'd figured out the opacity, which went from 0 at the beginning to 1, sorry, from 1 at the beginning to 0 at the end. So we kind of, the progress is actually 1 minus this. Yeah, right, like, do you know what, shall we just round down and see how it looks? And if it looks steppy and jerky, then maybe we can play around with like some more fancy stuff. I've done this before at some point, so it's probably why I messed around with. Interpolation is the fancy term for like this sort of blending of things like this. Let's do a first pass and just round down. Yeah, let's be lazy. So in processing, if we want to read a particular pixel from an image, we need to do a bit of somewhat fancy stuff first, which is when we load an image. So normally what happens, kind of conceptually, when we load an image is, wow, I really need to remove some of this stuff. Let me... What happens in principle when you load an image is, you have like your RAM and you have like an image file on the hard disk somewhere, and that just gets loaded into like some chunk of your RAM. And then if you want to access and read individual pixels in the image, it's just a matter of looking at the right part of your memory. But with modern PCs with graphics cards, you've actually got your your super fancy, I can't draw, fancy graphics card, and that image has probably actually been loaded straight off into your graphics card somewhere, so it's no longer like sitting here like easily ready to be accessed. It's in some super fast, efficient bit of memory on your crazy liquid-cooled graphics card. So in order to say, hey, I actually want to access this image directly, make sure I have access to those pixels and you haven't just shunted them off somewhere, there's something you need to do in processing, which is to use something called Yeah, you need to call this load pixels function. Then you can access the pixels just like they're an array. And then you call up date pixels at the end to kind of say, hey, I'm done with this. You can give it back to the graphics card to do what it wants with. So what I'm going to do here is, before I draw anything, we know that all the particles in this system are using the same like lookup image, so I'm just going to say load the pixels before we do our drawing stuff, and then say at the end, hey, we're done with it. And this is yeah, I mean, it will. That's kind of why this is necessary. But we know we're never actually drawing this image. It's worse. What's worse is if you're updating the pixels manually like this and then sending them back to the graphics card like every frame. That's something that can take time. In this case, since we're only reading them, it's probably not going to be an issue, and we're only doing it like once, calling this like once for each particle system. Could probably even just do it once at the start of the program and then just call update pixels at the end, or like not even bother. Yeah, but it's mostly if you're making edits that it's kind of an issue. So the pixel we want to look up is progress multiplied by the color lookup dot width. So that should give us that pixel. And yeah, for now I'm just gonna like cast that to an integer, effectively like rounding it down. Okay. Now we need to actually pull the color value out of the lookup image at this position, which is pretty simple to do. All we need to do is say color lookup dot pixels, and we just look it up based on its coordinate. Now this would actually be more complicated if the image had height. If it wasn't just 1 pixel high, we'd need to work out based on the x and y like where in this array the pixel is. And actually, if you check back in the recording, which is on our YouTube channel, of the like test version that we did of this kind of stream, where we did a this kind of dynamic ink spill effect, we got into this whole thing of how you calculate based on the x and y like where in this array you need to look. But for now, since it's just a sort of flat, 1D image, this all should work for us just fine. So now all I need to do is, can I just do this? Yeah. I think we may be done. Let's see what happens here. Okay, so this is almost working. So we're seeing the color spectrum here, kind of doing what we want, right? Like start off white, they turn yellow, and then kind of orangey, and then kind of reddy, and then black, and then they kind of fade out. And honestly, I'm not seeing much like steppiness and jitteriness in these colors, so maybe we don't actually need to worry about that more fancy interpolation. I mean, what we could again, I'm all for being cheaty and hacky. One thing we can just do is we could just if I just take this image and just like scale it up, then we can have our image editor like do this for us, right? It's kind of I kind of feel dirty and bad doing this, but honestly that will work just fine. I mean, that gives us a pretty nice kind of spectrum there. So going back to our processing sketch, you may have noticed that things don't look quite the same. And if we watch one of these particles, you'll see that actually they're just weirdly kind of popping out of existence. Like something weird's going on here. And I think it may be the case that we're not accounting for the alpha in this color. Let's check this out. Yeah, I mean it's a really dirty trick, to be honest, but you know, this is all smoke and mirrors, no pun intended. Yeah, these look to be fading out a bit more naturally now. So this kind of looks weird because I reduced the density of these a lot. That seems okay. So we've kind of got our embers now. Let's position these things a bit more kind of artistically again and see how the combined effect looks. Okay, I think the alpha is now like way too high for these main particles, so let's go back to their thing here and be way more aggressive with fading these out. Okay, this is kind of cool. But our embers are definitely not moving in a very like natural seeming way. I think that's kind of pretty plain to see right now. Like they're all moving in straight lines and there's no kind of relation to each other, so I think we need to do more to kind of fix that. One thing I feel like they should be moving upwards a bit more quickly, so let's do that to begin with. Okay, what I kind of want to get into now is... oh. Interesting. So we probably went like slightly off the end there. So let's just kind of clamp this. another thing you might notice is that the whole thing looks kind of weird at the beginning, and then over time it kind of smooths out and starts looking a bit more natural. But when everything is first spawned and is like floating up from the bottom, it looks really odd. So something I often like to do with particle systems is to kind of do what I call like a pre-warming, where I kind of pre-generate and pre-simulate and move everything before I ever show it for the first time. So I think it might make sense for me to do that here as well, to kind of get them up to speed before we ever kind of show it to the player. So a way to do this is just to update these a few hundred or a few thousand times to kind of simulate time passing before we ever kind of see them. So then once they appear, they're already like good to go. Ooh. And there we go. Okay, that looks a bit more natural now. We don't have that weird transition in kind of thing going on. Okay, so to make these embers move a bit more naturally, there's... Yeah, right, like this is the kind of thing, just with experience of doing a load of these, you realize that you need to do kind of some of this stuff to make it work. So to have these move more naturally, is everyone, or is anyone familiar with the idea of Perlin Noise? Is that something you're used to working with at all? In fact, let's go on image search and look this up. So Perlin Noise is this thing which is invented, unsurprisingly, by a guy called oh, okay, Blazing Fish. No worries. Maybe I'll wait for 30 seconds for you. But Perlin Noise is this kind of very typical, kind of natural-looking, cloudy, noisy effect, which a guy called, I think it's Ken Perlin, invented. I want to say in the 70s, I'm not sure, but this was in the early days of like computer graphics and VFX stuff. And it's often used for making textures for all sorts of like natural things. But the way I intend to use this is to use this kind of noise as a way to affect and apply some forces to these ember things as they're going around. Like, maybe that's kind of confusing, but hopefully it makes more sense as I dig into it. Let me copy this actually. So I'm not going to get into how this is generated. Like maybe that's another video for another day, but it's kind of possible to generate this noise, and in fact processing gives you this noise function which will do it for you like right off the bat with no trouble. But something kind of cool you can do with this, I guess you could call this another cool trick, is that where are we? We can use this to generate, I guess, something you'd call like a vector field. So what if, for example, we split the world up into like a grid? And don't worry, I'm not going to do this for the whole image. But Blazing Fish, if you want to refresh, now is the time to do it. Okay, so we split the world into this grid, which I'm mercifully not going to draw the whole thing off. We can then look into this noise at each point and use this to kind of generate a essentially a vector, like a direction, right? So we can kind of, so this kind of goes from like black to white. We could say, let's say black is like pointing straight up, and then like as it gets towards a mid-gray, we turn this arrow like more down, and then if it's white, it's, you know, it's back to like 360 degrees back to the top again, something like that. So, you know, maybe this point, if that's like a mid-gray, maybe it points like there. If that's black, then that's pointing like straight up. If that's like some kind of gray color, maybe it points there. The idea basically is that we can use this noise as a basis to generate a whole load of essentially random, but not like hectically random. Not like, okay, welcome back, fish. But not like hectically random directions, right? So, you know, if you take the point here and the point here, these arrows are going to be somewhat like similar to each other. It's not going to be like, you know, here's pointing this way and then here's pointing this way and here's pointing totally different direction. It will be a somewhat smooth field of all these arrows. And then when we take our embers, we can say, hey, I'm going to apply forces to it. Again, going back to that physics and acceleration and velocity stuff we looked into based on like where these arrows are pointing. Maybe this sounds super abstract and complicated, but as we go into implementation, hopefully this will make more sense. And I realize it may be a bad idea to try and do this right now. We're already a couple of hours in, but I kind of want to complete the effect, so it's great. We're going to try this. We're going to try this. So as a way of kind of demonstrating this, I'm going to step through the whole kind of screen, the space of the screen with a certain distance, so, you know, a certain spacing between these points. I'm going to call it 50 for now. And do the same kind of on the y-axis, so we essentially are stepping through this whole grid. For now, I'm just going to draw a little point at each location here. Make sure we've drawn a nice grid. Okay, so we created this kind of grid of little points. Like, I don't know if you can see these super well on the screen, but we've kind of defined this grid now. What we can then do is look into the world of Perlin noise at each of these locations. Okay, in fact, let's do something where I'm going to try and I'm going to try and visualize this noise based on the size of this circle, maybe. Okay, so we have a bunch of these circles which are somewhat random, and they're effectively sampled out of this kind of noise. So, you know, if this point aligns with a point on the grid and it's kind of a bright, then we're going to draw a big circle there. And if it's like a dark point, then we're going to draw a small circle there. One thing to pay attention to is the kind of scaling of this, and often... So the reason we're using Perlin noise instead of just generating a random number at each point is because we want, you know, points on the grid which are close to each other to have similarly sized circles. And we're kind of getting that effect here, but like maybe not quite. Let me actually drop this down so we can see in more detail there. Okay, so yeah, so you can see Perlin Noise is giving us this kind of clustering, right, where points which are nearby have somewhat similar sizes, and it somewhat like smoothly transitions into a low point and then like a high point and then a low point. We can kind of scale how we're looking into this noise field to give this the right sort of density or like spikiness or smoothness, right? So if we effectively like shrink down the coordinates we're sampling, then we'll get a smoother effect, if that makes sense. Let's have a look. Oh, no, didn't do that. Thank you, Blazing Fish. I was really worried that I'd gone off on a crazy tangent which would make no sense to anyone. And this introducing Perlin Noise at like 3 hours into the stream is kind of a risky decision, but hopefully this will make sense. If we reduce these numbers even more, then the noise will be even smoother looking. Right, okay. Hopefully you can see that kind of smooth effect going on here. So ultimately what we're going to do with this is use this field as a way to like nudge these embers around, right? So that they follow kind of these channels in this noise field, which is kind of similar to the way, I don't know, what is it that makes an ember really fly around the air in that funky way? It's probably like different air pressures and densities and temperatures kind of cause it to follow this crazy path like through the air. And I think for this size of image, this like density of stuff feels about right, like in terms of how we want these embers to move. So that's kind of what I'm trying to land at with this, tweaking these numbers here. So getting this ellipse is one thing. What we actually kind of want to do is turn this into an angle instead. So, not 260, there are 360 degrees in a circle. So instead of drawing an ellipse, what if we now draw a line kind of pointing in whatever direction this is going to indicate? So I've just realized I'm going to need to explain some trigonometry stuff now, which is not ideal. So I'm trying to visualize like more like these arrows now. So if we have a certain angle, so if we're starting at this point, if what I want to visualize is an arrow like this, right? If this is the angle we've chosen, I know the start point here is just going to be x, y. And let's say I've kind of used this random field to like generate an angle for me. I'm going to call it A. Mathematicians won't like that, but they'll have to deal with it. To work out where the end of this arrow should be, there's a little bit of trigonometry, so maybe I'll just give the answer here. Basically, like the sine function, if you guys remember this, the sine of A is equal to, this forms a triangle, right? This thing here. This is the hypotenuse of the triangle. And sine of A gives you this opposite side over the hypotenuse in terms of length. And then the cos gives you this side here. The adjacent side, I definitely should not have called this A. Mathematicians call it theta. I'm going to do that. Oh, this is getting messy. So the cosine of the angle is equal to the, yeah, SOHCAHTOA, right? That's exactly what this is. Sine is the opposite over the hypotenuse. Cosine is the adjacent over the hypotenuse. Yeah. So typically the way this works is given, you know an angle and you want to find like an x and a y. So what this boils down to is times, how long is this going to be? Let's call it 20. Okay, hopefully what we've managed to do right here is a load of, whoa! Okay, these should actually be offset from the X and Y start points. Also, I should probably draw this in like a red color or something like that. So one slight issue is that this angle is in degrees, but generally speaking on a computer, sine will expect stuff in radians, so this should not be 360, this should be 2 times pi. Again, this is a mathy thing which I don't super like having to explain. Okay. Hopefully this is now visualizing something which makes sense. It's not line either, it's stroke. Sorry, this is a hot mess right now. Okay, finally, there we go. So what we've managed to do here is take a Perlin Noise field, which we can't see directly, but we've used it to generate a load of angles, and it's created these paths or channels. Yeah, this is cool, right? This is a nice kind of effect. And what we can do is say, hey, given, say, this little particle here, which is moving along, we can look up the angle in this sort of field of vectors, this field of arrows, and we can nudge it in that direction. And that will kind of cause these to like follow these lines, right? And that's a very natural, like fire, embery like path that these things will ultimately follow. We're going to tweak some other stuff, and actually it would be useful to have this down the line. So I'm going to disable this drawing for now, but I think I may... Something else I often find myself doing is adding like a debug mode. Or more accurately, like a debug draw. Everyone loves developer debug draw stuff, right? And I'm going to draw this if my debug draw is enabled. And I'm going to say, maybe whenever I click on the canvas, I'm going to toggle that debug draw. So hopefully now what this allows me to do is have this off or run. Cool. Okay, so now we've got this field of lines. How do we actually apply this to these embers? Well, thankfully, with this ill-conceived like gravity thing we threw in, we've actually already got the basis for most of this stuff going on. There's a few like hard-coded numbers here, which I'm going to put out quickly into variables, I think. In fact, it's mostly just this noise scale thing. Cool. So very similar to what I'm doing with these lines. Inside the particle itself, I'm going to kind of do a lookup into this field of arrows to figure out which way I want to nudge the particle. I feel like that should probably depend on certain particle systems we maybe don't want to do this for. So I'm going to have another variable here for, let's call this noise field intensity. So how much of an effect this field will have on this particular particle, or, you know, this particular particle system. Because maybe we want the smoke to be like slightly affected by it, or maybe we want the embers to be like really strongly affected by it, or maybe it tanks the performance so much that we don't want to turn it on for the smoke because there's more smoke particles than there are embers, you know. So by default that's going to be at 0, but for this one thing, I'm going to set it to, again, like some sort of arbitrary value of 10 right now. Okay. So the interesting thing about acceleration is that while position and velocity kind of persist like frame to frame, right? Like you have to remember what your position was last frame and what your velocity was last frame, and those will like change over time. Acceleration is not quite like that. Acceleration is defined only by the forces you're feeling on yourself, like right at this very instant in time. So typically what you'll do is acceleration will kind of be zeroed out at the start of each update, and then we'll just say, hey, what forces are acting on me right now? Like maybe there's gravity, maybe there's this influence from this vector noise field that we've made, and that's the acceleration right at this instant, and then that's what affects velocity and in turn affects position. But we don't need to like store acceleration and remember it. We just calculate it from scratch every time. So that's effectively what we're doing here, right? We're initializing it to 0 in the x direction, 10 in the y direction just for the mass, and then what I kind of want to do is say if the noise field intensity is not equal to 0, then I want to look up the noise value at this particular particle's position. Again, we can calculate the angle, and then what I kind of want to do is apply a force in the direction of that arrow that's scaled according to this intensity. So if it's 1, then it's just going to be, the angle tells us the direction basically, and this is going to tell us like how intense the force is going to be in that direction. So the way this will look is we can reuse some of this. It's a very similar thing to what we did before in drawing those lines, right? So if we know that the noise is pointing in a certain direction, and we know, this is now our noise field intensity, like how much of an effect this field is going to have on this particle, that will kind of scale this arrow appropriately. Because by default, if you just do like sine of the angle, then it's kind of just has a length of 1, kind of by default. Do the same with y. Oh, good. Thank you. Thank you, Fish. Like when I go on about these things, I'm never sure if people are following or if it's clear at all. So let's see if we can notice some effect happening here. Okay, what I'm probably going to do is I'm going to, just so we can check this, I'm going to really ramp up this effect high. I'm going to really reduce the spawn rate, but increase the lifetime so we have more of these things and we can kind of follow them around. This is something where there's a lot of tuning that can be done to make it kind of feel right and natural. Yeah, probably because some of the forces down here happen to be like pushing them down. Yeah. So maybe I will drop this again. In fact, let's start spawning them higher up as well. Okay, I've realized I've got cosine and sine backwards, so everything is like yeah, that's true. Like right now the intensity is kind of always the same. Something else we could do is we could also have the intensity like vary across space, if you like. Yeah, I mean, in fact, you know, there's a way to do that. There's some other really, really cool stuff we can do, which is that, yeah, Perlin Noise is not, doesn't just have to be 2D, right? There's such a thing as Perlin Noise in 3D as well. I wonder if there's a visualization of this. Right, kind of like this, right? So as well as, you can think of this as like a slice through like a cube, and it has this kind of density inside of it, and one way we can get a really cool, yeah, this is awesome. One way we can get a really cool effect like this is to not just sample with an X and Y, we can also just put in like a Z here. And a way we can do that is have something that maybe the Z changes over time. So I've kind of got this global noise Z variable, which is kind of messy, but this should work for the most part. And what we'll see now, that's kind of slow. Let's ramp that up a little bit. Is our little arrows like drifting around over time? Yeah, this is really cool, right? Like there's so many, yeah, it's like biological. That's kind of the exact idea behind Perlin Noise, is that it's similar to the kind of noise and distribution of stuff that occurs like naturally in nature. So Perlin Noise is like this infinite space of these like values which we can pull slices out of or kind of move through to create these awesome like warping, moving over time things. Yeah, and it's pretty cool. So I think we're kind of close to wrapping up. What I'm going to try and do now is tweak some of these parameters a little bit so it looks a bit more presentable. So we have like a final product. And then again, if anyone has any questions, I will do my best to answer those for everyone. Yeah, I could spend all day tweaking this stuff, honestly. Oh, blazing fish. That's a very good point, actually. Something we could try is... Yeah, currently all these little embers are rotated at the same angle. So I think there are probably two ways we could go about this, right? Like, one is that we could just give them all a random angle to start with, or we could try and be a bit more fancy and rotate them to face in the direction they're currently moving, so they'll kind of like steer around. I feel like that's probably more accurate to how embers move, so... Yeah, I like that idea. I think I think we'll try and make that happen as well. Okay. So again, this is something I explained in the previous video about that ink spill effect, but in most types of 3D rendering, okay, let me step back a bit. So what I kind of want to do is just say, hey, I want to draw this image like rotated to a certain angle, right? But processing and a lot of these tools like don't give you something like that out of the box. So you need to use a rotate function to do that. The issue with these things is that typically what they will do, if this is our like canvas and this is like 0, 0 up here. If I have this ember, which I kind of want to rotate, you know, to be facing like this angle, if I tell it to rotate, it will always kind of rotate around the 0 point, which is really not what we want to happen. So the way around this is to effectively conceptually kind of move it to here and then rotate it and then like move it back. It kind of sounds a bit janky. It's just to do with the way that 3D rendering like works with these typical kind of rendering APIs. And since we're doing a lot of like moving and rotating, we kind of want to not have that rotation apply to you know, the next thing we draw as well. So there's a kind of like save and restore way that you can call this thing called push matrix, which is like, hey, I'm going to fiddle around with the rotation and scaling of stuff. And then you'd call pop matrix when you're done, which kind of resets everything back to normal so that the next stuff you draw isn't also rotated by the same amount and stuff like that. So typically what you would then do is, rather than drawing this at x, y, do something which kind of seems a bit odd, which is you would draw it at 0, 0, but then call a translate to move it where you want it, and call a rotate to rotate it how you want. And let's just try don't know, like a random number for now to make sure I've got this right. Okay, so we got some kind of rotation going on. But what angle do we want it rotated to, right? No, there isn't. Like, so, yeah, the question is there a function with like a pivot point parameter? Like some engines and APIs will give you that, but processing doesn't, and a lot of things don't, because that's just generally not how like the graphics cards think of these things. It's more like you set your position and rotation and transformation, and then you just draw something and that gets applied to it. And then yeah, there are benefits to it, like if you've got objects like nested inside each other, like if you've got a car and then someone in the car, if the car's rotated, you then want the person in the car to be like positioned and rotated in relation to that, so you can use them to create these like hierarchies of things inside each other. That's kind of part of the reason for it, but it's kind of just a quirk of like how these APIs work, to be honest. So the question here is, how do we determine this angle? And I think what we want to do is base this just on the current velocity. So you were talking about Sokotoa a while ago. We've done So, we've done Ka. This is where the Toa comes in, so the tan of an angle. Let me use my tablet here. Tan of an angle is equal to opposite over adjacent. Or another way to put that is the kind of inverse tan of an angle of O over A is equal to... God, I can't draw theta. What's going on? Yeah, and in programming we typically use something called arctan to do this, so... Cos tan y Vx. I believe this will do what we need. Now I'm probably off by like 90 degrees because, yeah. So that it's okay. You can kind of see how the angle is related to the direction it's moving, but it's kind of moving with the flat side forward, which is not exactly what we want. And that is because typically in maths, when we think of an angle, the angle of 0 is actually not like pointing north on the compass, it's actually pointing like east. And then like 90 degrees is at the top, 180 is back here, 270 is down here. So probably what we need is something which is kind of aligned like that way. Okay, that's kind of super long, but these don't quite look like embers now, but at least they're going in the right direction. These are moving faster, right? They would look like sparks or something, I guess. So often you come up with some effect that doesn't work for what you need it to be, but it will still have some use somewhere. So generally these are just almost there, they're just not quite fast enough maybe. So I could just have them moving faster to begin with. Maybe not living quite as long. Yeah, definitely in the realm of just fiddling around with stuff right now. So, I think we're pretty much there, right? Awesome. So I'll hang around for a couple of minutes if anyone's got any questions, but I think apart from that, we are pretty much done for today. So thank you everyone for tuning in and participating. If you're not following our Twitch channel, then please do. Like every other week we do a tournament, and I'm gonna, of our game Steamhounds, which this character the engineer is from, and then between those on the off weeks, I'm gonna maybe start doing these coding streams. We also have a YouTube channel, Stray Basilisk, where we're going to kind of cut these down and upload them over there as well. Yeah, so let me know if you've got any other questions, otherwise I'll just leave you looking at this guy for a little minute.